that from
See if it keeps going.
1 minus 27. Okay. Thank you.
All right, we're just doing a little more, so we'll see if it keeps going or not. Is everybody good with that? Okay. The last section in chapter 8, section 8.2, is the most honest section we've hit yet. So, chapter 8 is honest in the sense that we normally don't know mu, so we're trying to get a feel for what mu might be by creating these confidence intervals. But section 8.1 assumed we know sigma. Now, that is true sometimes. Most of the time, we walk into a situation and we don't know a damn thing. So that situation I'm talking about earlier where you go out to a forest and you find this new species of spider, nobody's ever seen this before. Do we have any clue about the standard deviation of spider weights for that species of spider? We don't have a freaking clue. We don't know if this is like a baby and the mama's coming around the corner, or if this is like grandpa and they're normally about this big. We have no idea. We have no freaking idea. So I take a sample and do the best I can. Are you guys with me? But I don't know mu and I don't know sigma. So if I don't know sigma, what's the next best thing for me to use, considering I'm taking a sample? What can I calculate if I take a sample of spiders? I can calculate the sample mean, and I can calculate the sample. What are the two things you always want to calculate? The mean, standard deviation. So I can get the sample standard deviation. So in A2, don't know sigma. We're not going to know sigma. If I don't know sigma, the next best thing is S. S is an approximation for sigma. If I take a sample, the sample mean is an approximation for mu. The sample standard deviation is an approximation for sigma. So, section 8.1, the formula was x bar give or take z sigma over square root of it. Now let me ask you this. 8.2, it is very obviously going to put an S here instead of a sigma because we don't know sigma. Are you guys with me? That part you guys could have teased out for yourself. I don't know sigma, I'm going to use S, so I'm going to put S in place of sigma. Here's what I want some help from you guys. You already said something like this earlier today. If there's anything in my situation that I'm less sure about, should my interval get bigger or smaller? Bigger. So the way I like to call it has to get bigger to cover my ass. So if I don't know something, I have to cover my ass for that fact. So my interval's got to get bigger. So I still need a normal distribution to do a damn thing, but I'm not going to be able to use z-scores. They don't go far enough. You guys just told me for any given situation, I need to go a little further than normal to cover my ass for the fact that I don't know how spread out the data is. So everybody's semi with that. So my formula stays fundamentally the same. It's got the same structure. I just can't use a z-score because it doesn't go far enough. So the person who invented this, very quick side note, anybody ever drink any Guinness?
Yeah.
Okay.
Who?
Guinness.
It's a beer.
It's like a beer where they put a full course of a meal into it also.
Yeah.
Basically.
It's the dark.
Like food?
It's the darkest, fullest body freaking beer. Huh?
They put food in
No, they
That's
don't,
not-
but it's as
a
if.
very dark, heavy beer that will.
It's like as if.
So why do people drink it?
Because Ireland likes it.
In grad school, I got to drinking it. I don't like Guinness too much, but my physics instructor did. And he would go to the bar, he'd get some Guinness. I go with him. A group of us would go with him. Because if he drank enough, he'd start telling us stuff about the next day about, what's going to be the test? I'm thinking about it. So,
And you've got a light beer just to kind of like.
yeah, well, I'm like taking the babyest sips of this thing, like, say it again, girl? Okay.
No way!
Yes.
That's so
What was his name? Dr. Klein. Every other word out of this man's mouth was the F word. He had, you've heard of somebody having a short fuse?
Oh, kind of like you and shit.
Very much. Very much. But a short fuse, you've heard of somebody having a short fuse?
Yeah.
Like
We always said he had an inverted fuse, like it was already in the bomb. So, I mean, he was just ready to go off any moment. But when he got some Guinness in him, he calmed down.
Dr. Klein, like
Dr. Klein.
one of the frickin' doctors from
Swiss guy, I loved it. He was like
like one
I
of the
didn't know
doctors
Jid.
from Old
Okay.
World Blues.
So, what this guy created, his name was William Gossett. He created a T-score. He was doing studies on, he worked in the Guinness Brewery. That's why Guinness came into this. And he was doing studies of his own on distributions of, I can't remember the specifics now, but I think it was the plant stuff they use. Is it wheat they use for that? Hops, yes. He was using distributions of different age hops and what it does. So the problem was, if he let the company know about his work, they owned it. So he submitted his work under a pseudonym. He called himself Student. So you'll often see this called the Student's T-score distribution. So these are called T-scores. So let me give you this. How many more charts do we have this semester? One more. Okay, and we got one more chart after this.
So due to things that are unknown, you're gonna use T-scores instead of Z-scores.
Yeah, if I don't know, don't worry about it. If I don't know the population standard deviation, I must use T-scores instead of Z.
Are we double checking?
I mean, you know, as much as we're ever done with anything.
Well, does that theoretically mean we got a quiz on every?
Yes, it does. Oh, pretty cool. Anybody has one?
Population standard deviation.
All right, so let's see what this means here. I always forget what I'm going to say before I give you stuff like this, but I'm pretty sure I got you ready for something that's on this chart. Do I have any paper left?
That's good. It's not blank though.
I got nothing. Thank you.
Yeah, multiple.
Thank you. Brownie points. I don't keep track of them, so it doesn't really matter. Okay. Degrees of freedom. I'm pretty sure I talked about degrees of freedom before.
No.
Do you remember the whole thing? All right, look, very truncated. I have three numbers. I know they average to be 10.
Oh, yeah.
Remember this?
Yeah.
If three numbers add to be 10, if they average to be 10, what do they have to add to be?
30.
30. Because the only way that three numbers can average to be 10 is if when I divide by 3 I get 10. 30 divided by 3 is 10, so they have to add to 30. So I can totally make up the first two things. And the last guy can be whatever it needs to be. So give me a number, any number. 12. Give me another number, any number. 18. Now here, what's that already added to be? 30. So what do I make this?
Zero.
They average to be 10. If somebody, I was waiting to see if anybody was going to tell me 1200.
Yeah, we did one with you having doing like -3 million.
Sure.
or something like that.
So if I make this 12 million, right, then I can make this negative 11,999,988. Because that would leave 12 plus 18 is 30. So I can make the last number whatever I need to, so the overall it makes 30. Are you guys kind of with me? So if I have, for three things, how much freedom did I have?
2.
2 degrees of freedom. So for n things, how much freedom do I have? N minus 1. So all degrees of freedom is for us right now, because later it's going to change. But right now, degrees of freedom is n minus 1.
Is that degrees of freedom squared? Is that 2?
That says equal.
Oh, is that an equal?
Yeah. There, now it looks worse. Okay. So, look at the very bottom of this chart. Do you see any numbers that look familiar at all?
Yeah,
1.965.
1.645.
Or what?
This one maybe not so much, but 2.33's come up at least once. 2.575 came up. This is a little bit more precise, to be honest. These are all z-scores, yes?
Yeah.
Okay. T-scores exist to cover my ass for when I don't know sigma. So T-scores were invented for situations, holy macaroni, for when sigma is unknown. If sigma is unknown, we use S, correct? When will S become a better and better approximation for sigma?
Larger it is.
The larger my sample is. When my sample gets really large, S and sigma will be basically the same thing. So when my sample size is large, I can just go ahead and use z-scores.
How large?
That's why they leave it as just large. It depends on how precise, it depends on how precise the specific thing you're doing needs to be. So they leave it as large, they leave it up to us to define that. But do you see how little it's changing? Down here it's changing very little. So basically most people's large is not too much above 2,000. You guys semi with me? I don't know if you guys are really with me. The smaller my sample gets, how do I feel about S approximating sigma?
Oh, it gets less precise.
Gets worse and worse, correct? So don't I have to cover my ass more and more? So the number I'm putting in instead of Z, if it gets bigger, that means it's pushing my confidence interval out more. And what happens to that number as my sample size gets smaller and smaller? It gets bigger and bigger, and when it gets really small, it's like, you better freaking go weigh the shit.
Well, it jumps
Hell yeah.
from 9 to 63.
How big of a sample is this? Careful. 2. 2 minus 1 is 1, so degrees freedom. So this is a sample size of 2. That's not worth shit.
It's not much of a sample. You sampled 2 things.
Yeah. It's kind of related to, I don't want to say that. That is a huge jump, I agree. But with a third data point, that actually triangulates things. That's why there's such a huge jump here, but that's still, 9 is still stupid big. So, what time is it? Okay. I'm going to bring that next time, but let's do one example real quick. What about a sample size of 37? Believe it or not, that's a 3. Jeff, stop looking at the monitor. Okay. Sample size of 37. I want to be 90% confident. And I know that, I don't know sigma, I only know S. What t-score will I use? First off, why am I allowed to do something? Why am I allowed to use Z or T?
Because you don't have.
And
No. Not why do I have to use T, why am I allowed to do something?
N's over 30.
Yes, N is bigger than 30. So it's normally distributed. So I don't care if you're using Z or T, it's got to be normally distributed. So this is normal, N's greater than 30. Now here's the other thing, how do I read, so now I know how to read this side, where am I going to stop here?
37.
No?
36.
36, good. N is 37, degrees of freedom is N minus 1. I'm going to stop at 36. But what column am I going to look at? Look at all this shit. Now, when I make a confidence interval, chop, how many tails do I make? 2. And I want to be how confident, did I say?
90.
90%. What's alpha? What's alpha?
10 and 5.
10%. Alpha is the area and the tails or tail.
Oh,
So there's
combined.
10% in the 2 tails, yes?
Okay.
0.10 and 2 tails. Now, what if you say there's 5? If there's 10 and 2 tails, there's how much in 1 tail?
5. 0.05.
Same column, yes? So I start in this column and I stop at the degrees of freedom. What did I just say?
Start in that column.
This
stop
column
at
here.
degrees of freedom.
Stop at 36. And that is the number I would put in. Instead of 1645, I would put in 1688. I need you to really understand. All the frickin' work we would do for section 8.2 is the same as the work for section 8.1. It's just I'm using a t-score instead of a z-score. So I'm just putting a different number. It's all the same work we did. I'll get the error, I'll add, subtract it. I'll make my little statement. We are such and so confident, right? All of it stays the same. I just get the number I use from a different chart.
How would we know which one's
Oh.
correct?
You ready? If I want to be 95% confident, there's 5% outside in two tails. If I want to be 80% confident, how much is in two tails? If there's 80% in, there's how much out?
20%.
20% in
So
two
for
tails.
now, we're only gonna use area and two tails.
So the last thing I want to say today is why is there this option? Because in chapter 9, we're going to be doing hypothesis tests. So one claim we could make is something like stat students that have a class in the morning have a higher average than in the afternoon. You guys go with me? Greater than. I think the stats are greater than the afternoon. So I'm only interested in one direction then. Well, for you guys, sorry, this way. I think that they're up. I think they're higher than the average for the afternoon. I think they would be up from it. That would be a one-tail test. If I said the average for the morning is different from the afternoon, that could be bigger or smaller. That would be a two-tail test.
Oh, but you said higher, so it's only one side of the.
So in chapter 9, we're going to see one-tail tests. We're going to see two-tail tests. And the awesome thing is, I'll just go to the right freaking column, right row, and then I'll just stop at the right number. Yes? You guys kind of with me? And again, this is new, I understand. So next time I'll have what I call a lightning round. We're going to look up a bunch of T-scores. Notice something very quickly. What if I said I had a sample of 117? What would their degrees of freedom be?
You're gonna round down, I guess?
Yeah, 116, so we round down to 100. We always, when there's something we don't know, we make things worse for us. So I would make the T-score bigger.
Oh, so you round down.
Yeah, so do you see on the chart I go up?
What if it was like 180?
Oh, the closer you get to 200, the more you can use this one, because it doesn't really switch that much, but yeah, okay. All right. I've reached my limit anyway today, I think. I'm feeling mostly better, but obviously not completely.
Get well soon, Professor.
Huh?
Get well soon.
Yes, that's the plan.
I forgot what I was doing wrong. Professor,